Right. Okay, so welcome back. So this is the second part. We're now going to talk more about some of the core techniques or key techniques in the record linkage process. More looking at the traditional way, how things have been done and still are being done. So again, I mentioned before, I showed you this slide a few times. So we basically look at each of the steps and some of the core aspects of those, right? Starting with data pre-processing, moving on to blocking, indexing, how we compare things, how we classify, and at the end, how we evaluate how good the linkage is. So let's start with data cleaning. Why do we need this? So if you've ever worked with real data, most of you must probably have, we know real data is clean or are dirty, as you call it. So we often have typographical errors, nicknames, variations of the same spelling because people don't know how things are being spelled. That's a big issue with names and addresses. Because we don't really have a single true variation of a name. So I'll give you an example of Gail. If I ask you, there might be 3 or 4 different types of spelling variations of Gail, and they're all correct. The same with addresses. That's a big issue. We might have different coding schemes that can be as simple as male, female, 0, 1, but can be fairly complex across different domains. We're likely going to have missing values. Again, for a variety of reasons. There might be missing middle names, missing address pieces. Who knows what the reason were. And of course, data is changing over time. Addresses are changing, names are changing, somebody gets married. Nowadays, even gender can change, which doesn't leave us a lot to compare with in the worst case, right? Names and addresses are especially prone to such errors because often they are scanned from handwritten forms. They're typed in, handwritten, recorded over the telephone. So there's all different types of ways of how data can be entered. And as shown in the third lecture, we draw up a diagram at some stage with a student of what are different ways of how data can be entered. Each of those will result in different types of errors. So typing errors are different to OCR errors, are different to phonetic errors. Again, we need to know often, if you know how data is being recorded, we can customize algorithms to deal with these mistakes or variations. Then of course the same person provides details differently. They might be known under different names to different people. You might have a nickname. Everybody knows him as Bob. But his name is Robert, so if he talks to the taxation office or to the government, his name is Robert. Everybody else just writes down his name as Bob. He might even use Bob when he orders a book from Amazon, for example. So we have these variations of nicknames, right? And as I mentioned before, there's different ways of how things are being spelled, right? And none of them is wrong in many cases. So what do we want to do in data cleaning or data pre-processing? We basically want to convert our raw input, which potentially could be a long string if it's historical data, here's an example address, into a well-defined set of small fields or attributes, we call it in the database community, right? So if you have an address such as that's address string such as the one at the top, we want to extract all the bits and pieces of information. We want to extract, this is an apartment, we call it a flat type in Australia. 3 is the flat number, A is the flat number suffix. Then we have 42 is the, what we call it, that's kind of an Australian standard, that would be the street number. We have main being the street name, RD is the road, Canberra is the locality, ACT is the state, and 2600 is the postcode. If you imagine you have the raw data and you want to link records together, you're not going to get high accurate linkage results. On the other hand, if you have all these little fields here, for all the records you have in your databases and you link them individually, and we try to calculate similarities between these individual attributes or fields, you get a much higher linkage quality. So the cleaning step is basically we want to remove unwanted characters, so punctuations, slash, quotes, whatever we have. We want to expand and correct abbreviations, and we potentially want to correct misspellings as well, right? Then we want to segment the address, and same as a name, into these well-defined output fields. And then the last step, we can even validate if an address actually exists. So in Australia, Australia Post provides a database of all known addresses in Australia. You can check, is there a main road in Canberra? It's probably not, right? I'm not sure what's in UK and Scotland. If you have a database which you could purchase potentially, which can validate and verify if an address exists. So how do we do this? Traditionally, people have developed rule systems. So we have rules such as, if I go back here, if an address starts with a word which is not a number, then look up that word in a lookup table of flat or street names and things like that. So app would be an abbreviation for apartment. We can identify this if we have an external table of all different types of apartment words, right? If an address starts with a number, and after the number there's no second number, then say that is the street number. So there's a lot of complex rules. And when we started this work in the early 2000s, we actually got a rule system, a commercial rule system, which was used by New South Wales Health. So that's the health department in New South Wales, Sydney, and the surrounding areas, the whole area, the big area of New South Wales. And that rule-based system for addresses contains something like 2,000 rules, taking care of all the strange rural area addresses in Australia, and there are lots of strange rural addresses in Australia. And people basically manually developed this rule system over years. And each time new data came in, new addresses came in, which couldn't be, which weren't covered by these rules, they had to refine the rule system. So this is a very time-consuming, complex process. You need to know exactly how these rule things work, what the language is to develop rules, etc. So much rather, we want to have something probabilistic. We want to have something where we can learn what is an address, what are the different parts of an address, what are the output fields for these addresses. So we've done some work, and others have as well, based on something which is called the hidden Markov model, which some of you might have heard about. So I show this at a very high level, the basic ideas of how this works. So these are probabilistic models, so they assign values to certain output fields. They might not get it correct all the times, but they're very flexible, and they're also very robust. What we, however, need is training data. So it's kind of an algorithm which learns, and I'll show in the next slide an example. So we need to have a set of true, correct addresses in this format here. So we basically need to have maybe a few hundreds of these addresses already segmented correctly. But it turns out this is pretty straightforward. This can be done in a few hours. So this is an example hidden Markov model. So what it basically shows us is it's a way to go from the beginning of an address to the end through a sequence of states. Right? So hidden Markov model is also used in speech recognition, where we want to assign individual words or phonemes of a sentence or a word to different parts of a sentence. So let's say we have trained that hidden Markov model, we get these transition probabilities. So this tells us that if we have an address, in 90% of the time, it started with a street number. After that, in 95% of the time, follows a street name. So we have 42 Miller Street, for example. So the street type is afterwards. But we also had 8% of the addresses which started with a street name. They didn't have a street number. We also had 3% of addresses which had a street name which is made of 2 words, things like that. So you can imagine you have an address, you segment it into these fields, and now you want to assign every word in the address to one of these states here. So if you have 42 Miller Street, the most likely 42 Miller Street, Sydney 2000, for example. You will most likely assign the 42 here, Miller here, Street, Sydney, 2000, end. If you have Sydney, New South Wales, 2000, then it will go locality, territory, postcode, end. So we train the model on example data, which we know is clean and standardized, and then we can apply this model on unseen data. Right? So we learn these probabilities from training data. That's kind of the supervised learning approach here. So how would the whole process now go? The first step would be what we call cleaning. We have certain lookup tables where we correct misspellings, expand abbreviations, like RD becomes road, ST might become street, maybe, maybe not. We remove unwanted characters such as quotes and backslash and things like that. And we might misspell, correct misspelling and things like that. So now we have kind of a cleaned string. Now we do what we call tagging. In that step, we separate that string of that text string of words into individual tokens. So basically, we separate everything at the white space, a space character, right? So that gives us a list of words, numbers, and separators. I'll show an example on the next slide. And now we assign each of these tokens with a tag. And again, I'll show an example on the next slide. So a tag could be something like street. The word street will be assigned, this is a known street type. 2000, which is Sydney's postcode, will be assigned, this is a known postcode. Miller or Maine would be assigned, this is a known street name, and things like that. So at the end of this tagging step, we end up with a list of words or tokens, and each of them has assigned one or several tags. And these tags we give to the hidden Markov model. And we're using the tags instead of the individual words because there's thousands of or tens of thousands of different street names. The tags are a much, much smaller domain, as we call it. Right? So let me show you an example to clarify this. So let's say we have the raw input address, which is 42 Mayor Road in Cooma, which is a little town about an hour's drive south of Canberra, which has a postcode of 2371. The first step is we clean it. The only thing we clean here is we make everything lowercase, and we replace RD with the word road. That's kind of the expansion of the abbreviation. With RD, it's pretty clear that this has to be road. With ST, you have to be more careful. ST could be street, but it could also be saint. Right? So in Australia, we have a town called St. Mary. I'm sure you have something similar here as well. Right? So an ST could be something street in something called Mary, or it could be something street in St. Mary. So we have these ambiguities as well. Now we do the tagging. So we split this text string into the individual tokens at the white space. So the first one will be 42, Mayor, Road, Cooma, 2371. And now we're using lookup tables and specific rules, which are a very small number of rules, to assign a tag. So tag tells us something about the type of that token. So for example, 42 is a number of length 2. Mayor is SN, means it's a surname. So we found Mayor in a surname lookup table, which we've extracted from data. And it's also a token of length 5, which only contains letters. Road is a street type, and it's a word of length 4, which only contains letters. Cooma is both a locality name, so it's a known town name. It's also a street name. There's a Cooma Road in another town, right? And again, it's a word of length 5, only letters. 2371 is a known postcode, and it's a value which contains 4 digits, so 4 numbers only. So now, we basically reduce, remember, we have millions of these addresses. We kind of convert all of them in these tags, and the number of different tags is much, much smaller. So we now can use those for the hidden Markov model, because we don't have to learn the Markov model on these tens of thousands or hundreds of thousands of addresses, but only on the much smaller number of tags. We give these tokens to the Markov model, which we've trained before, and that the Markov model gives us something back such as that, which basically tells us the 42 is the street number. We call it number first in Australia, well, in the database anyway. Mayor becomes a street name, road becomes street type, Cooma becomes the locality, so the town, and 2371 becomes the postcode. So such an approach is much more robust compared to having rules. If something is completely unknown, we did experiments on a large database of 1 million addresses or so. This probabilistic approach gets it right most of the time. it might not get the apartment and the floor and things in the front wrong, but because the structure of the addresses towards the end is very standardized, it gets these parts of the address right, which is important for geocoding. It doesn't matter if somebody lives at level 3 or level 5 in an apartment block, as long as we get the street number, the street type, and then the locality correct, we still get the right location. So a colleague of mine who's a geographer at New South Wales Health, he did an analysis on comparing a commercial rule-based system with that probabilistic approach and found up to 10% improvement by looking at GP addresses in Sydney and surrounding areas. So this is the way how we can standardize addresses, and we can do the same for names and things like that. The important thing is that we need to have values which have a sequence of tokens. So we're really making use of that known sequence that an address normally has a street number, a street name, a street type, etc., which I think is the same here in the UK. You have kind of a standard. So we end up with a very nice, clean database where every word is assigned to a specific field. And then we can do the linkage based on those. And that improves quality a lot. Right. So let's move on to the second step, which is the blocking, indexing, filtering, or searching step. So now we have our two clean databases in the same format, so the same attribute structure, all nicely cleaned. What are we now going to compare? We don't want to compare every record in one database with all the records in the other database. So if you have 1 million records in one database and 5 million in the other, that gives us 5 trillion record pairs to compare, which even a bigger supercomputer would crunch quite a long time nowadays. There's also no point in doing that. If we assume that none of these two databases has duplicates, so there's only one record per person in each of these two databases, then the maximum number of links or records we should link should be 1 million, right? If this database contains records about 1 million people, and this database contains records about 5 million people, then we should only link 1 million records, if we assume there's no duplicates in the databases. Does that make sense? Right. So we want to find 1 million links out of 5 trillion potential comparisons. That's less than a needle in a haystack, right? That's maybe a needle in 100 haystacks. So I don't know what the comparison is, but it's what we call a very imbalanced problem. And the performance bottleneck in record linkage is often the detailed comparison. Right? So it might take only a thousandth of a second to compare one pair. But if you have to compare 12 trillion, it's still going to take a long time. So the aim of blocking or indexing is to not compare records which never going to be the same person. So records which are completely different. We don't have to compare John Smith, who lives in Edinburgh, with Mary Miller, who lives in London. There's no point they're going to be this. There's never going to be. Well, okay, it's very, very, very unlikely that they're going to be the same person. Right? So that's what the idea of blocking is. We remove as many of these pairs out of the 5 trillion we have, so we don't have to compare them in detail. Of course, we want to make sure that we don't lose in that process, we don't lose any true matches. Right. So if John has changed his gender to be female, has moved from Edinburgh to London, and the date of birth is the same, yes, then we're going to lose that person in that example. Right. So traditional blocking is what again has been developed in the 60s as part of the Felice and Santra approach. We basically look at certain attributes or fields in our database and only compare records which have the same value. So an example might be, we know that postcode is often a highly accurate, potentially highly accurate attribute. Let's just compare people who have the same postcode. The nice thing with postcode also is that it's often, the number of records in a postcode is roughly evenly distributed. So we can do that. We only compare the records which have the same postcode. The problem with that is if somebody has moved, we're never going to compare that person. Right? So we have to do that with different iterations, so not just postcode, but maybe also surname, maybe the age of people, etc. So that's the first problem with traditional blocking. We have to do several blocking criteria, as we call them, or blocking keys, and compare records in different steps, such that if there is a wrong value in postcode or somebody has moved, we're going to compare them because they have the same surname, or we're going to compare them because they have the same age and things like that. Another problem we have with this traditional blocking is that the blocks generated depend on the distribution of values. So if I use surname, again in New South Wales, we have something like 25,000 people called Smith. If I use surname by itself, I'm going to compare all the Smiths with themselves, well, not with each other. And again, 25,000 squared is quite a large number. Again, that doesn't make sense, right? So maybe I only want to compare the John Smith with the John Smith and the Mary Smith with the Mary Smith. On the other hand, I only have 4 people called Dijkstra. Does anybody know who Dijkstra is? You guys, you know that? Okay. The computer scientist. Dijkstra was a theoretical computer scientist from a Dutch person. It's kind of a very unusual name in Australia. There's only 4 in New South Wales, right? So you're only going to compare the Dijkstras with the 4 Dijkstras. Well, if they're the same person, then I'll find them. I don't have to do many comparisons. But I don't want to compare all the Smiths with each other. That gives me, again, a big problem. So I kind of try to find blocking criteria, or blocking keys, as we call them, which have an even distribution. And that's where postcode, for example, in Australia is fairly uniformly distributed. I don't know how it's here in the UK, that every postcode has roughly the same number of people living in it, which is nice, but actually that's a challenge as well, because Australia Post changes the postcode distribution on a regular basis. If too many people live in a postcode, they move the boundaries. There you go, right? So you can't use postcode if you link over time, for example. Right, so one way we can overcome data quality issues in blocking, again, if you might have different variations of names, if you just use surname for blocking, we're not going to compare these variations. So Gale and Gale, the example from before, or Dixon and Dixon, one with CK, one with X, are not going to be compared. So we do something which we call phonetic encoding. So these are small computer programs which basically take in a name and return a code. And the idea is to bring names which sound similar assigned in the same code. And these techniques are actually not new. SoundX is one of the first, was developed in 1918, so almost 100 years ago. Again, there are people, I think, in census who try to kind of block their handwritten, their paper-based census forms and put all the records which have the same SoundX into a big pile, right, and things like that. A second example is the New York State Information Interchange System, which was developed by the New York police in the 40s, I think, again, to try to find criminals who change their names or have name variations, right? So what they basically do is an example, set of examples. So you have input names, you apply these phonetic encoding functions, and out comes a code which groups similar sounding values together. You can download free implementations for all these phonetic encodings from online repositories. So just search for SoundX, you get online examples, you can download Java code, etc. So you can see that SoundX, for example, keeps the first letter and then converts vowels into digits. The New York code keeps a double metaphor, which is a more recent one. They only keep letters, but they all convert a name into a much shorter code depending on how they sound. And they're pretty successful. So you can see, for example, Steve and Steven have the same codes, well, almost the same codes here. Gale and Gale have the same SoundX, and the same, everything is the same. A problem with SoundX is that it keeps the first letter. So Christine, Christine, and Christina, the first letter makes a difference in the code. Right? So what people often do is they reverse the name, basically they reverse the name string and do SoundX on the reverse string. So the idea is that if they're similar at the end, we get the same code. Things like that, right? So these are very useful to block similar sounding names into the same block, right? So the Smith and the Smythe we compare those, right? And therefore we can overcome some of the name variations which otherwise we wouldn't compare. And this can be, these phonetic encodings can also be used in the comparison step as well. Okay, so now we've looked at the first two steps. We've cleaned our databases, we've done blocking. So now let's look at the two potentially the most critical steps, the comparison of the records which are in the same block, and then the classification. They're kind of interweaved. The first thing we need to look at, these are pretty dense slides here, approximate string comparisons. Right? So again, we still have Gale and Gale, or Smith and Smythe. In computer science, we could do what's called an exact string comparison. Basically, character by character. If they're the same, then we give them a value of 1, which says they are the same. If they have a character difference, then we give them a numerical value of 0. So that's kind of, we calculate a normalized numerical similarity. But instead of just saying this is the same or this is different, so 0 and 1, we want to assign some form of similarity. So Smith and Smythe might give us a similarity of 0.8. Smith and Miller give us a similarity of 0. Gale and Gale should give us a similarity of 0.9, for example. So we want to calculate these similarities for all the attributes, so all the fields which we generated before. First, street number, street name, street type, postcode, etc. We compare each of these fields individually and calculate similarities for those. There's many different techniques available. There's about 30 different types of string comparisons. Some for specific types of values, such as names, others for longer strings, others for numbers, etc. I'll just show you two examples of how we do this. So one is we're looking at what we call Q-grams. So we basically extract short substrings from, let's say, a name. So if we have Peter, and we want to look at bigrams length Q, we have what we call a sliding window. So we extract 2 characters and move forward. So Peter becomes P-E, E-T, T-E, E-R. Right, so that's fairly straightforward. We just slide over the string, the text, and we extract these substrings. So we do this for all names in the database. And now we can compare these lists, so these sets of Q-grams, right? The example then, where do we have Pete? Okay, for Pete, we only get P-E, E-T, T-E, so not this one here. We can basically count how many of these substrings do 2 names have in common. And that's what we call, there's different techniques. One is called the dice coefficient. So we look at this formula here, where we basically say 2 times the number of Q-grams in common divided by the sum of how many there are. So if you have Peter and Pete, then 3 Q-grams are in common, P-E, E-T, T-E. So that gives us the common 1. Peter has 4 Q-grams, Pete only has 3. So we end up with a similarity of 0.86 using this approach here. And that's a standard technique that's being used not just in record linkage, that's also being used in natural language processing. Google is using similar techniques. When you type in a search query and you make a typing mistake and Google recommends things, that's exactly the same. Well, it's kind of more sophisticated, but the basic idea is looking at these Q-grams here, right? So we get a similarity between 0 and 1. For Smith and Miller, because they have no Q-grams, do they? They have no Q-grams in common. We get a similarity of 0. For Smith and Smith, we get a similarity of 1 because they have the same Q-grams. Another technique which you might have heard of, again, commonly used in text processing, is edit distance. And the idea here is basically, what is the minimum number of keystrokes you need to do to go from one word to another word? So let's say I give you a word, and you have to type to convert this word into another word. Right? So that's kind of the number of edits you have to do. So an edit is an insert of a character, a delete of a character, and substitute of a character. Sometimes it's also including transposition of 2 characters. So we count. So we basically have an algorithm which encodes the 2 words, and we count what's the minimum number of such edits we have to do to get from one to the other. I'll show you an example on the next slide. Actually, let's just go forward and show the example and then come back. So this is how we would do it. So here we have Gale and Gale. So we build such an edit matrix. That's what the algorithm does. And now we look at, this is an empty string. How many edits do we need to go from one string to another string? So an empty string, from an empty string to G, means we have to insert 1. We have to type G. From 0 to G, we have to type 3 characters, right? To go from GA to GAL, we have an edit of 3 because we have GA. You only have to type in Y, L, and D, right? So we built this matrix basically row by row, and the diagonal or the bold, if you can see the bold diagonal here, that's the minimum edit distance we need. And down here in this corner, that's the final minimum number of types of keystrokes, roughly, we have to do to get from GAL to GAL, right? So here it's 2, so we have to change the I to the Y, and we have to type the E, and that gives us the 2 edits. So this is what called edit distance. Again, very common in computer science when we look at text and looking at, spelling correction is an example which is based on techniques such as that, right? So where they look at, if you type something in on Word or whatever, wriggle red underline saying this is a mistake, it basically looks up these tables, which is the most likely correct word it knows in a dictionary, which has the minimum edit distance, right? So if you do a right click on a word it doesn't know, they often order according to the edit distance. So that's very similar techniques as well. So now we have a distance, right? So the more different two words are, the larger the distance is. So we again want to convert this back into a similarity. So if I go back a slide, and we can easily do this. The larger the distance, the smaller the similarity. Right? So we do a conversion here. We have 1 minus the distance divided by the maximum length. Because you know a distance cannot be longer than the length of the maximum length, right? So again, that gives us a similarity between 0 and 1. Coming back to this example as before, Peter and Pete have a distance of 1, so we get a similarity of 0.8, which is different from the similarity I showed you before, right? So here we have a similarity of 0.86. That's really a point I want to make. There's many different string similarity techniques out there. They don't all generate the same similarity for the same strings. Right? So there's no correct similarity. Generally, the more similar words are, the higher the similarity is. But depending which algorithm you're using, you might get slightly different numerical values, right?
Quickly ask, is it weighted by the length of the string? Because basically, if you have only
yes.
2 letters,
yes.
you only need 2 letters.
That's right. So at the moment, it's weighted through this equation here, where we divide by the maximum length, right? But it's subtle, right? In a way, if you have very long strings, you get a very high similarity if you only have 1 or 2 edits. Well, if the strings are very short, you get a much lower similarity. It's kind of a percentage of, compared to the length of the strings, what's that's this equation here, what's the difference we have, right? If it's 1 character out of 2, then we get a 0.5 similarity. If it's 1 out of 10, then we get a 0.9 similarity. So something like that, right? That answers your question. So, yeah. And in fact, these techniques, this edit distance-based approach, is also being used in computational biology. So if you have worked with genomic sequences, the BLAST algorithms, which compare long genome sequences, work on a very similar principle. So instead of having the strings being names, the strings are becoming the genome sequences. And they're very similar looking at changes, how many inserts of genomes and how many changes, right? So it's again, all these underlying computer science algorithms. Right, so keep in mind that now we have techniques which allows us to compare our data, and we end up with similarities between 0 and 1, right, for each of them, depending on how similar the values are. So we looked at that. Now, let's have a look in more details about that probabilistic record linkage approach, which was developed in the 60s. I think it's almost the same slide as before. So the idea really is now we compare the attributes which we have. So addresses, names, dates of birth, etc. Using approximate string comparison. We also have approximate functions for for dates. for age and things like that, where we kind of look at how different are two age values, and we can calculate a percentage difference and things like that. We even can do geographical similarities as well. How far are two addresses, and the further away they are, the less similar they are, things like that. So we're basically calculating these weights for all the attributes, and then we sum them together. I'll show you an example in the next few slides, and then we classify. The problem with this approach is it requires estimating of errors in the data, and I'll give you an example as well, in order to calculate these probabilistic matching weights. Felice and Sandra, this approach also assumes independence between the attributes. So a similarity on first name is independent on the similarity of the last name. Or more generally, first name and last name are completely independent of each other, which of course is not true. Right? If you have an Asian first name, it's more likely you have an Asian last name. Certain street numbers and certain street names are more likely in certain geographical regions and things like that. But despite these problems, that approach is still widely used. So what we're doing is basically we compare records, as I showed in the example here. In the first step, we get the similarities between 0 and 1, right, using as approximate string comparisons. And then on top of that, we multiply them with the amount of information contained in the attributes to give us these what we call the matching weights, and explain on the next slide how we calculate those. Right. Generally, in the Felice and Sandra approach, a positive weight tends to tell us this is an agreement, this is the same person, the record's about the same person. A negative value means they are different people. Right? So it's a disagreement. So in the example here, Dr. Mr. Yeah, could be the same person, right? So we give it a small weight. It doesn't tell us a lot. Peter and John, different names. We calculate the negative weight. That tells us they're not the same person. Paul and the missing middle name, we don't know. We assign the value of 0, which means it doesn't tell us either agreement or disagreement. And the surname is both Miller, but it's a fairly small positive weight because Miller is such a common name. So it doesn't tell us much that this is the same person. So on the next slide, I'll show you the example how we calculate these weights. So now how do we go from such a vector of matching weights to our classification? So the Felice and Sandra approach basically sums these numbers together for every compared record pair. That gives us one number. If the number is highly positive, then it tells us this is an agreement. There's people who have similarities in all attributes. If the sum is negative, that tells us this is not the same person. So what I tried to show you down here is a histogram of, we've done this over thousands and thousands of record pairs. We get normally a kind of binomial distribution where we have up here, so these are the sums of these matching weights. So up here, record pairs which have a sum of 20 are highly likely going to be the same person because they need to have positive values in all of the attributes, right? Over here, we have the records which have negative values everywhere, so they're different in all the attributes, and that's going to be the majority here. Lots and lots of records will have negative values everywhere. In between, and we have these two thresholds, we have the potential matches, where we're not sure. We might have the same name that gives us positive weights, different date of birth gives us negative weights, different address gives us negative weights, right? So we have this area where we're not sure, and these are the record pairs which are given to a manual clerical review, where somebody manually looks at them and manually decides that's a match or that's a non-match. Okay. So the question is now, how do we get these from the simple string similarities? How do we get these matching weights, right? So here's a very simple example to show you what is the information. We basically need to know the amount of error we estimate a certain attribute. With an attribute, I mean a column in a spreadsheet that our field has. So let's assume we have a month of birth in our database. So that's values between 1 and 12, January to December. Let's assume we know there's a 3% error. So the person who gave us this database, the person who recorded information, they know there's roughly 3% error in this database. Sorry, in this month of birth attribute. Right? Okay. So in order to calculate a match weight and a match agreement weight and a match disagreement weight, so basically in order to calculate values which we could use here for an agreeing month of birth and a disagreeing month of birth, we have to do a few assumptions. So let's assume we know which records are about the same person. Okay, the first thing is, let's say we grab 2 records from the database where we know they're about the same person, because there's a 3% error in the database. We know in 97% of the time they're going to have the same month of birth. Everybody agrees with that? It's getting toward lunchtime. Okay, so let's say I know I grabbed 2 records from a database. I know they're about the same person because we have an error rate of 3%. In 97% of the time, the month of birth is going to be the same, right? Because of the 3% error rate. Okay? So we call that the link agreement. That's the Felicien-Santer terminology. Right. If you now grab another pair of records, we know they're about the same person. In 3% of the time, they're going to have a different month of birth because we have a 3% error rate. But there's also the issue that they can both be wrong and we get the same, but let's assume that's very, very unlikely. So we have the link disagreement, which is 3%. For the same person, in 3% of the time, they have a different month of birth. Okay, now we got 2 numbers. We need 2 more. Now let's say I grab 2 more records, and I know they're about different people. In 1/12, they're going to have the same month of birth. Right? If I ask randomly 2 of you to do lots and lots of time, in 1/12, you're going to have the same months of birth because we have 12. And assuming that births are uniformly distributed, which we know they're not, etc. But in 1/12, so in 8.3% of the time, 2 records from different people will have the same months of birth. So we call that the unmatched agreement. It's 8.3%. The last probability is what's the likelihood that 2 records from different people have a different month of birth. That's of course 1 minus the 8.3%. That's 11 out of 12. That gives us a 91.7%. Right? So again, if I randomly ask 2 of you what's your month of birth, in 91.7% of the time, you will give me different answers. Okay, so now we have, and that's the unmatched disagreement. So now we have these 4 numbers, the link agreement, the link disagreement, the unlink or the unmatched disagreement, the unmatched agreement. And based on that, we can calculate the agreement weight as being the link agreement divided by the unlink agreement. And we do this in logarithmic space. Again, that's developed in the 60s, so where they use logarithm to kind of, it's much easier to work with those. We also have no issues with numerical, with calculation. So that basically means the agreement weight is 3.54. So if 2 records now, as we link them, have the same months of birth, we give them a positive value of 3.54. The disagreement weight is the link disagreement weight divided by the unlink disagreement weight, which gives us a negative value of minus 4.92. So if you have 2 records and they have a different month of birth, I give it that negative value. So these calculations are based on the assumption that we have a 3% error in our database. If the error is larger, the calculations change. If you do the same on day of the month or year of birth, then we have again different calculations, right? If you want to do this for surname, we also have to take the frequency into account as well. So Smith and Miller are more common, so the likelihoods are going to change compared to rare name. So it's a fairly complicated thing, very specific to the content of the different attributes which we have. Right. Actually, just going to spend more time on this. So this was developed in the late 60s, or the 60s in general. Felicien-Santer actually proved that under certain circumstances, this gives us the optimal way of how we link records together. But it has the problem of we need to know the error rate. I'll come back to this here. We need to know the error rate, which is very difficult to estimate. Finding optimal thresholds for the upper and lower. So where do we decide what is a match, what is a no-match? What are the potential matches is very difficult. The assumption of independence. And then, of course, the whole issue that we link, so we sum all these numbers together into one single number. We're losing a lot of information here. So every record is represented by a single number. If it's positive, it's a match. If it's negative, it's a no-match. And if it's somewhere in between, it's a potential match. So most of the computer science research in recent time actually uses the whole vector of individual numerical values, because that tells us much more about do people who have the same name are more likely going to be matches than people who have a different name and things like that. So I'll talk about this after the break. Okay, so a few more slides about, I think three more slides about evaluation. So now we've basically gone through the whole process. We've cleaned the data, we've done our blocking, we compared records, we classified them. We want to know how good are we? That's the most important thing if you want to employ this in practical applications. So what do we need to measure? The first thing we can measure things such as the computational complexity of how fast did we do. So we could measure runtime, we could measure how much memory we used, etc. But that is very system dependent. So we want to have measures which are independent of the computing system used. So the first thing is to look at linkage complexity. And the most common used measure here is what's called reduction ratio. This assumes basically we have done blocking, and reduction ratio measures how much of the full 5 trillion before, remember for the example, how many of these complete quadratic comparison have we actually done. Right? So it's basically the number of candidate pairs which our blocking generated, so the number of things which you're actually going to compare, divide by the potential number of all record pairs. The smaller this is, the larger the reduction ratio gets. So a higher reduction ratio means we've reduced the complexity of the process a lot. A reduction ratio of 0.5 means you're still doing 50% of all possible comparisons, which you don't want, right? Then the second major thing which we can measure is how many of the true matches are actually in the candidate pairs. So that tells us something about how good is our blocking. So our reduction ratio doesn't need anything to know about the true match status, pairs completeness, and then the linkage quality measures. They need to know about the true match status. So they need to know the truth. So pairs completeness measures how many true matches have gone through blocking. How bad was blocking in removing true matching record pairs, which we don't really want to have, right? This could, for example, be measured by randomly, not exactly randomly, but sampling a subset of record pairs and manually classifying them. That gives us an estimate of how many true matches have we missed, right? There's another one called pairs quality, which tells us about the goodness of the candidate pairs. How many true matches do we actually compared to how many candidates we have in total. That only tells us, so these two measures tell us something about the goodness of our blocking with regard to computational complexity and with regard to the linkage quality. It doesn't tell us anything about the final outcome. To measure how good we are with regard to the linked records, we need the truth. As I mentioned before, this is very difficult to get, right? We also call this gold standard, the ground truth, which is very difficult to obtain in many applications. Now there's two different types of errors which we can have when we link records together. The first one is we might, and that comes back to a question from before, we might miss a true match, right? So we have two people, but they've changed so many of their details, and we've done something wrong in our blocking, we miss them, but they're the same person, right? So that's kind of a bad thing. We call this a false negative or false non-match. The other thing is, which could be potentially even worse, we link two people together and say that's the same person, but they're actually not. An example is twins, right? We say they're highly similar, same surname, same date of birth, same address, we link them together, but if actually they're two people. That's a false match, or It's also called false positive in machine learning in the classification space. Right. I mentioned before when I talked about blocking that we want to find out 1 million true links out of the 5 trillion potential record pairs. Right? So we call this a very imbalanced problem. There's a lot of true non-links. Every record in one database is a non-link to almost all of the records in the other database. Right? So that's what we call true negatives, true non-links. Only a very small number are true links. So we're going to find that needle in the big haystack, right, of which records are actually true links. Right? So even after blocking, it's not unusual to have a class imbalance of 1 to 100. That you still have, for every match which is in the records which we compare, there's going to be 99 or even more non-matches. It's still very imbalanced. And many machine learning techniques who learn the characteristics are struggling with such imbalanced class distributions. So you might be familiar with accuracy, which is a general way of how we measure how good a classification is, which is basically calculating how many true matches do we have and how many true non-matches we have. Or how many false non-matches and how many false matches divided by all the potential matches. If we use accuracy in that definition, we get very high accuracy values. You get 99.99%, simply because there's so many non-matches in that space. But it doesn't tell us anything about how good the linkage actually is, right? So, so accuracy should not be used for measuring record linkage quality. Right? It's not meaningful at all. What we use instead are two measures which are also used in information retrieval, so web search. So when you query something to Google or Bing or whatever, you get a set of results back. And there's two measures which are being used in that domain. The first one is precision. So how many of the results which you get back from the search engine are relevant? And the second one is recall. How many of the relevant results did you actually get back? In record linkage, precision is how many true matches are in the set of the classified matches. So again, you've compared things, you've classified, these are the matches, these are the non-matches. How many of the matches which you found or classified as matches, or how many of these record pairs are actually true matches? That's precision, right? It's the number of true positives divided by the true positives and the false positives, the number of records which we link together, which we shouldn't have. Then we have recall, which is basically measures how many true matches did we find from all true matches. This takes into account how many matches didn't we classify as matches. Right. So that's, again, the true positives, so the pairs which we classified as being a match, divided by the true positive and the false negatives, so the ones we missed. Right. And these two measures give us a much better picture of how good a linkage actually is. It's compared to accuracy. And it's 12 o'clock. And it's time. Questions before?
We usually know these as sensitivity and specificity.
Yes. So they have lots of different names in different domains, and I don't know all the names. And that's right. It's just, I always get it wrong with the mapping, so I don't even try. Yes, me too. Yeah. Okay, so that was the traditional stuff so far. Are there any questions on any of these techniques? Everybody's hungry. Yeah.
Can I ask just a very basic question?
Yeah.
How does the system manage when people change their names, but they are the same person?
Yeah.
And when the name change can happen quite frequently?
Does it? I don't know. So again, it depends on what
I'm thinking of children, in public care sometimes, or
right.
Children.
Okay. I guess again depends on the actual domain, right? So we're developing the algorithms, we're trying to take care of these things, but this depends on domain to domain, right? If you know that your names are changing, then potentially you can add that information into the weight calculations. Right? As you say, well, if name changes all the time, we don't give high matching weights to the names. So then we look at maybe date of birth and give a much higher weight. Right? So these weight calculations can be calculated assuming there's no domain knowledge at all, or they can be the basis of some domain knowledge-based linkage, which is often the case. But that's when it's very application specific, right? Where you, the domain expert, tells me, don't worry about names. So we still look if names are similar, that still tells us a story, but if names are different, then we might not give it a negative weight at all, right? There has been a bit of work in looking at temporal aspect. That's very, very recent as well. If we know that, and we've done a bit of work in that area as well, if we know that 20% of people, let's say 20% of people change their names every year, if we have 2 records and we have the time when they were recorded, the further back in time we go, the less important a name should be. Because if you go back 5 years in time, almost everybody has changed their name. Right? So we developed techniques where we look at this temporal decay and modify the weights according to that. But again, that's very, very domain specific. And it's actually also very challenging to get enough information to build a proper statistical model to actually tell us that. So maybe you can use information from a statistic agency which tells you how often people change names. But it's, again, that's researchy type of things.
Hi. I was going back a bit earlier as well. You had the examples where you were using the blocking and you were putting it through. One of the techniques was the sound X to get, and then you moved on to using the Q-grams, but you were back using people's full names again.
Yeah.
Would you use the Q-grams with the blocked result rather than someone's name? Would you use it with the sound X result rather than the person's
Again, this
name?
is very domain dependent. But that's where, depending on how you know what the quality of your data is, you will play around with different techniques. So I can't give you I don't want to give you general advice, and then you go out, I was using SoundX because this guy told us to use SoundX, right? So that's where, if you have some form of truth data, so let's say you have a sample of where you have, let's maybe 100 or 1,000 pairs of records where you know they are the same people, you could do experiments, right? You could say, well, let's play around with different techniques of blocking, of the string comparison, and which one gives us the best results, right? But it's very difficult to give general advice, I think. But it's often a combination of techniques. I mean, what we often do is if you have different, just last week in St. Andrews, we tried to link historical birthdays and marriage and census data together. I've actually developed a code which uses something like 300 different blocking keys, just like kind of combinations to try to bring all the people who potentially have some similarity together in some form, right? What we often also do is we compare surname not just once, but we might just use 3-4 different types of similarity calculations. So that gives us 5 similarities for surname, 5 for first name, 5 for address, etc. And then just use a machine learning technique to kind of find what are the best ones. So that's kind of, I'll talk a bit more about this after the break as well. But I can't give you, use this or do that. That's maybe wrong. So.
Hopefully a quick question. With the methods for getting names that sound like names, presumably if you've got data that's been encrypted, that's going to, affect being able to use those techniques.
So the question is about what if names are encrypted? Can we do the same? We can't. If names are encrypted, you're completely lost.
Yeah.
I talked about this in the last part of the workshop. Once names are encrypted, you can't use any of these techniques. You end up with random strings of things, and there's no similarity. That's the whole point of the encryption, right? So, and that makes it challenging, right? So we have to have access to the real names and addresses at this stage to do the comparisons. Some of the privacy-preserving stuff does work on not on encrypted data. We have to have the real data which we encode, and there's a difference, at the data source, and then we only use the encoded information. But if you have encrypted information, you can go home or have lunch.
Thank you.
A question? Yeah.
When you give information on precision and recall, is that very kind of domain specific? So is that kind of something that kind of you publish for Australia, but it's completely rubbish for Glasgow, for example, even if you use exactly the same method?
Good question. Again, I don't even know what would be good results for certain type. I mean, it's very difficult to compare the data, right? Because I mean, the data in Australia would be different from the one in the UK, from Scotland, from America. There's so many influences. I guess ideally you want to achieve both high precision and high recall. I mean, if you get numbers below, again, don't quote me on this, 80, 90%, it tells you. I mean, if you get a recall below 80%, which means you're going to miss 20% of the true matches. So they're not comparable in a way that one number on one data set means this is good, this is bad. If I have a really messy historical census database and I know it's incomplete and the transcription is bad, then maybe I'm happy with a recall of 60%, right? If I link contemporary government data and I get 60%, I wouldn't want to use that, right? If I'm a national security agency and I get a precision of 10% or 80%, or I get a recall of 80%, that means they're going to miss 20% of all the terrorists, right? So it's so they're very difficult to compare. Again, they're very domain and application specific, these numbers.
So do I have to validate every linkage that I do?
What does validation mean? I mean, in a way, again, it comes back to the challenge of we don't know the truth, right? How do you know what is the truth, right? Unless you actually go back and call these two people, are you John Smith in the taxation database? Are you the same person who lived at this address 3 years ago? Did you have that operation in that hospital? Do you want to do it more? You can't do this, right? Because you have to do this on a large scale. We can't do that, right? Again, that comes back to that really challenging thing. We don't know the truth. So even things which are called the ground truth or the gold standard, I think we shouldn't call it gold standard. If it's based on manual assessment, we should maybe call it the silver standard or something like that. So we simply don't know what the truth is in many application areas. I'm not sure if that answers your question, but yeah.
Sometimes you're matching sets of records where you have Sometimes you're matching sets of records where you've got 500,000 and 500,000, and you're pretty sure that there's a one-to-one correspondence. Yep. Can this theory be fixed to improve things that way? Because you could potentially get the one person matching more than one of the other.
That's right. Again, I come back to a bit. Well, actually, I don't cover this one-to-one thing because it's another issue which is more advanced in a way. If you know that it's one-to-one, there's different ways of how we can do this. I mean, you can basically say in a very greedy way, we calculate the similarities and we just grab two records that have the highest similarity and say that's the same person. Yeah. And then we take the next two, the next two, the next two. But that doesn't give you the optimal overall assignment. So this algorithm, which called assignment problems from graph matching, which give you an overall optimal solution. They're very complex as well, right? So, and again, it comes back to if you know that you have to link everybody with one person, one record in one database with one record here, you must probably never going to get it correct, 100% correct. But how do you know how good you are? So the whole area is very vague sometimes, right? Unless you again know the actual truth, you might just link the wrong people together. And once you've done one mistake, that then ripples through, right? So once you've linked those two, then the ones who actually are the true links you never get, right? So it's a challenging. It's more like it's not a technical question. I think it's more like the question of where does the data come from? What do we know about
ordering would make a difference, because if you start off with a really bad match, it could be matching something that could have been a bad one to somebody else.
There's a potential other way, right? But you look at if you have human resources, you do give links to people and ask them to manually assess them, right? But that's very costly. So again, very domain dependent as well.